Hi guys, today we're gonna talk about solving a heat transfer problem. So the question we have here is a spherical shell of uniform thermal conductivity. So it means the K constant is the same all throughout the shell, and it has an inner radius of 1 meter and an outer radius of 2 meter. At 1 meter radius, the temperature is 100 degree, and at 2 meters, the temperature is at 0 degree. Sorry, make a typo here. And the question is, what is the temperature at the radius of 1.5 meter? So first, we're gonna draw um, a graph. Okay. So this is, let's say, it's a spherical shell. This is the inner radius, Ri, and then this is the outer radius, Ro. So let's say at the outer radius we have a temperature of 0 degree, and then in the radius we have temperature of 100 degree. And then so at the radius of 1.5, what is the temperature? So first we gonna we know that heat transfer that happens in the spherical shell is heat transfer by conduction, because it's a solid. Heat transfer through solid, so it's by conduction. So we can have Q equal to negative K A dt dx. So let's analyze each variable. So K is constant, and Q is also constant because in steady we assume steady state. And then so the area, we can have area equal to 4 pi r square. That's area of cross sectional area of a sphere. So we can substitute that value in. So Q is negative K is constant, by the way, times 4 pi r square. And then since in this question we use the variable that's changing is r, as it's going from the inner radius to the outer radius, we can have dt over dr instead of dx. And then we're just gonna solve this um, with the integral, and then we're gonna find the value for q, or at least a simpler formula for substitution for q, and we'll find out later why we need this to do the step. Okay, so let's do it. So this is a uh, first order differential equation, and then we're gonna solve for t using separation of variables. So let's do this. We're gonna move q q is a constant, so we're gonna separate temperature in r radius. Okay, so we're gonna do this. Oops, sorry. Q divided by, let's put the negative sign here. K 4 pi r square times dr equal to dt. So just separate those variable, and we're gonna put the constant on the outside. Okay, so and then I'm gonna put the negative sign over to dt as well. Q over K times 4 pi, um, 1 over R squared dr equal to dt. And then we can have boundary for this integral. So since he is traveling from the inner radius to outer radius, it's gonna go. It's gonna be like this: ti at the bottom, and then to at top, and same for radius, ro and ri. And then we're just gonna substitute a value in and solve it. So this is the integral. Oh, I'm sorry. I think I marked this wrong. This is supposed to be R O, and then R I. Totally wrote this wrong. And then we're gonna do this. R O R I equal. R O is 2 meter. R I is 1 meter. And then integral of dt is just t, put negative t. To is 0, ti is 100. So just gonna continue down here times negative. So I'm gonna keep solving this. K 4 pi equal to 1.2 times 100. Therefore, oh, I don't think you guys can see it down here. I'm just gonna go on to the next page. Q over 4 pi k times 1/2 equal to 100. So Q 4 pi k is equal to 200. So Q is equal to 800 pi k. And then, so this is how we got the formula for Q, and I'm gonna show you guys why it's important. Because when we trying to when we're trying to find the temperature of at R equal to 1.5, we're gonna do the same. We're gonna apply the same integral over here. I'm just gonna copy this. And then when we want to find, we're gonna use, instead of the upper boundary, instead of using the outer radius, we're gonna use the radius at 1.5 meters. It's gonna be 1.5 1. So this is where we run into the problem. If we skip the first step, we don't know what the value for a temperature at 1.5 meter. So we're gonna have an extra const variable that we can't solve. So let's see, Q 4 pi k times 1 minus 1.5 negative plus 1 equal to 100 minus 10. So see, right now we have this unknown variable q and unknown variable 1 t equal 1.5. So that's why that we need the previous step to plug q, to substitute q to get a value. So as we did before, q is equal to 800 pi k. So we're gonna do this 800 pi k go to 4 pi k, and then this one is, I'm gonna get my calculator real quick. I'm so sorry. 5 is 1.3 equal to 100 minus temperature at 1.5 meter. And so we cancel out pi k, and then 800 minus 4 is 200 over 3, go to 100 minus temperature at 1.5. You guys see over here? And then I'm just gonna write up here. I'm just gonna move this up here. So we have t 1.5 equal to go to 33.3 degree Celsius. So we needed the previous step where we have the data for, because in this question we weren't given the value of k, so we wouldn't even be able to know. But if but we can always cancel out k, and so if we find the value of q of the heat with using with the with the constant k, we can cancel out the constant k and pi in second integral problem. That's why we cancel out pi and k in the first place. But yeah, this is how we do this heat transfer problem. Thank you so much for listening.